So I have a couple new things to discuss. Baz, this is going to be for you. You'll see where I have some stuff for you to look at concerning the graph. You'll see. Deuterium and hydrogen. Now, deuterium has a neutron and a proton in the center, or at least that's what it's accepted as. Then you have an electron in the outer regions. And hydrogen, you have one proton in the center and an electron. Chemically, these are similar because they have one valence electron, but nuclearly they're different. The deuterium basically weighs twice as much as the hydrogen. And to get that across, I'm 192 pounds. Doubling my weight would make me 384 pounds. That's crazy. This giant dude. But that's the difference between deuterium and hydrogen. Deuterium is a lot heavier than hydrogen. It's double the weight. And a lot of other elements, their isotopes are much closer together. And that's very important to realize. It's because, sure, there might be O16, O17, O18, and all those three are stable isotopes. 17 and 18 are stable too, but the difference is not that much when it comes to their mass, because they only have one or two extra neutrons. But when you have the DH ratio, the extra neutron makes the element twice as heavy. That's like basically making, just imagine if gold was twice as heavy, you know? Instead of having a density of 19.1 centimeters per gram, it would be 38, or centimeters per gram. Yeah, gram per centimeter cubed. It would be 38 grams per centimeter cubed. So double the weight. That would be crazy. That's why it's such a special ratio. And I got incredibly lucky with the fact that I figure this is very important for determining the ages of objects. And the papers where I outlined the understanding is right here. Starting with Venus, Baz, this is very important. Venus is aged with DH ratios as opposed to the Earth. Just to give an outline, the DNH ratio for young stars that sit very, very early right here, the DNH ratio is very low because it hasn't had a lot of time to separate out the lighter from the heavier hydrogens, the deuterium from the hydrogen. So you'll have one deuterium per maybe 100,000 hydrogens or maybe 1,000,000 hydrogens. So it's 0.00000001 as the ratio when you factor in that 1 over 100,000 or 1 over 100 million or a million. But as the star ages and cools, the heavier deuterium stays and the lighter hydrogen escapes. So that ratio goes up. Now it's still a fraction, but it does go up significantly by many magnitudes. And for this example, an ocean world would be 1 deuterium per 10,000 hydrogens, so a magnitude of 1, which is an enormous increase. And then the Earth, I had a typo here. I put 1H over 6,250H. I have to fix that right there. But it should be 1 deuterium over 6,250 hydrogens. And I saw another paper where it had 6,711 hydrogens, but about 6,000, 6,500 is a good estimate for the Earth. That being said, you take that and you can have other objects in here. I have Venus in here. You take that and you can figure out how old an object is by measuring the other objects' ratios. So for Venus, I had originally thought that it was about 25 billion, easily double, if not more, than the Earth's age. But when I take Venus's DH ratio, which is between 1 deuterium over 62.5 hydrogens to 1 deuterium per 40 hydrogens versus the Earth's 1 deuterium over 6,250 hydrogens, what we find out is that the ratio is 100 to 156 times higher. And that says a hell of a lot, because it means, in essence, Venus, by its measurements, is at least 100 to 156 times older than the Earth. And that is incredibly, incredibly old. I had to take out a few days and just ponder over where this is going. And then it started to like come together slowly and slowly. And one of the important ideas here is that I was looking at dead stars as just being dead. You know, oh, once the star dies, who cares? And I was like, wait a second, that isn't a good viewpoint, because when you look at dead objects like a paleontologist would or a forensic scientist would, dead just doesn't mean dead and then it stops aging per se, because the material does decay, its radioisotopes to decay, as well as there are other features involved such as fossilization, which can differentiate something that's recently dead from something that's hundreds of millions of years old, like Tyrannosaurus rex fossils or, dinosaur fossils. So to say a dinosaur fossil is in the same level as a Roman soldier that died in battle in the year 5, it's not the same thing. You have extremely old objects versus objects that are maybe tops 2,000 years old. And that's why I was like, crap, if Venus is so much older than the Earth, I have to differentiate between what's recently dead, what's kind of been dead for a while, and then the really, really, really old dead objects. And that paper, I think, that paper is already up. I'll link that. It's just Stellar Metamorphosis Dead Stars. And on the graph, I have here recently dead on that phase curve. This is the phase curve, that red line, that red curve. And you have mature dead, and you have ancient dead, and you have archaic dead. And I use words to differentiate them. I know it's not exactly a number, but that's kind of like to put in your mind that, yeah, you could be looking at Mars or you could be looking at Venus. They're both dead, but one is a hell of a lot older than the other. And for this talk, Venus sits not where we originally put it, Baz, but like right there. That's where Mars is, believe it or not. Mars would be right there, right below a little, maybe like make it a little dot right below Venus, where Venus currently is. But Venus belongs way the hell over here, where those dots are. And it's between 450 billion and 1.56 trillion years old. Venus is incredibly ancient. And to think about it like that, to think, oh wow, how could something be that old if all the scientists are saying, the Earth or the entire universe is only 13.7 billion years. Well, that isn't exactly a good rationale, because if you study history, if you look at James Hutton when he discovered his unconformity at Siccar Point and I think Scotland, he was battling against the young Earth creationists. He was like, the Earth just isn't 6,000 years old. And they were teaching young Earth creationism at Cambridge University. Knowledgeable, educated people believe the Earth to be max 6,000 years old. That's what they believed in the 1800s. Now, to look at, the educated people, what all the scientists believe, say, oh, that's correct. No, it always can change. when new information comes in. And this is one of those spots in history where new information has come in, and I've had to make a drastic change. We're moving away, similar to Hutton. Hutton moved the Earth billions of years old past 6,000 years. I'm moving the objects inside the solar system from 4.5 billion to 100 times older than that, if not more, depending on how much it's broken up. And Mars is in here as well. I use the DH ratios from Mars. This paper will be up pretty soon. I just put it on Vixar. That hasn't been uploaded yet, so you can't see it. But I have Mars between 21.33 to 68.1 billion years old, according to its DH ratio. And its DH ratio, I link that to the page too, is 7.58 to 10.9 for every 10,000 particles of hydrogen. And that's really important too, because Mars is way, way, way younger than Venus. So we have a solar system full of objects that are so incredibly old that the idea that they all formed in a single disk around the sun just sort of like, it disintegrates. The whole protoplanetary disk nebula hypothesis just flies apart, because you can't have objects this ancient around the sun, because they outdate the sun by hundreds of billions of years. All right, you guys, I guess that'll do for this talk. Later.